Hi, I'm Bob Pryor. Today I'm talking to you about sum and difference formulas for sine, cosine, and tangent. We want to first ask this question. Does cosine of A minus B equal cosine of A minus cosine of B? In other words, can we just distribute cosine to A and to B? Well, to answer this question, we're going to look at this and find a counterexample for A and B to demonstrate that it's actually not an identity. We're going to use A equals 180 degrees and B equals 90 degrees. So the cosine of A minus B becomes the cosine of 180 degrees minus 90 degrees. And we want to know, is that equal to the cosine of 180 degrees minus the cosine of 90 degrees? And that's a question. So we're going to put a question mark over the equal sign because we're not sure if it's equal or not. On the left side, we're going to simplify within. Of course, 180 minus 90 is 90. Cosine of 90 degrees on the left. On the right side, the cosine of 180 degrees is negative 1 and the cosine of 90 is 0. So negative 1 minus 0. And we still have that question. Are they equal? Left side becomes 0. Right side becomes negative 1, and the answer is no, they're not equal, because that's a false statement. In other words, cosine of A minus B equals cosine of A minus cosine B is not an identity. It's a legitimate equation, and there are certain values of A and B that it will work, but not always, so therefore it's not an identity. So what is the identity for the cosine of subtraction? Of a difference. And difference does mean subtraction, which is why we see called the cosine of a difference, cosine of A minus B. But what it's equal to is a product, cosine A times cosine B, plus another product, sine A times sine B. You'll notice that in the first product, there is an A, meaning the angle measure A is in each of those products, and the same is true for B. B is in each of those products. Except in the first product, it's the cosine of A. In the second one, it's the sine of A. In the first, it's the cosine of B. And in the second product, it's the sine of B. We can also consider the cosine of a sum. It looks very similar. Cosine of A plus B. Plus being a sum. Well, let's put this into action. Let's demonstrate that if we take some numbers that we're familiar with, like A is 150 degrees and B is 30 degrees, that when we put this into that formula I just mentioned about the cosine of a difference, becomes cosine of 150 degrees minus 30 degrees, is equal to, in fact, we're asking the question, is it equal to cosine of A, 150, times cosine of B, cosine 30 degrees, plus the sine of 150 times the sine of 30. What I'm trying to do here is to demonstrate that this formula works for some known values. We're still in question, is it true? I think we're going to find out that it is, but let's just follow this through. Cosine of 120 degrees is equal to cosine of 150 is negative radical 3 over 2. And cosine of 30 is positive radical 3 over 2. Sine of 150 is positive 1/2, and sine of 30 is also positive 1/2. Cosine of 120 is negative 1/2, and when we multiply these fractions on the other side, we get negative 3/4 plus 1/4. Are they equal? Well, let's see, negative 1/2 equals negative 2/4 when we combine on the right side. And that simplifies to negative 1/2, so yes, they are equal. It's true. That's just one example that demonstrates the cosine of a difference is correct. Now, we can write this cosine of a difference using a variety of symbols. But the key is knowing that when we see the cosine of A minus B, that the A appears in each of those products. Also, the B appears in each of those products. Whether we call it A, B, X or Y, alpha and theta, it doesn't really matter. Basically, it's the cosine of the first minus second becomes cosine of first, cosine of second, plus sine of first times the sine of second. Let's take a look at the similar and distinct features between the formulas for both cosine of a plus b and cosine of a minus b. Again, we have two products separated by a plus sign or a minus sign, and it starts off cosine a cosine b, and it ends sine a sine b. Notice, though, inside we have a minus sign, but outside we have a plus sign. Similarly, inside we have a plus sign for the cosine of a sum, but it is a minus sign outside. Now here we'll compare and contrast the sine of a plus b and the sine of a minus b. Notice again, it's two products. The first one sine a cosine b, and the second sine b cosine a. Notice that angle A appears in each product. First as the sine of A, second as the cosine of A. And angle B also appears in each product, first as the cosine of B, then as the sine of B. So the pattern here is sine A cosine B, and then sine B cosine A. As far as the operations are concerned, sine of A plus B, plus inside is also plus outside. And sine of A minus B, minus inside, is also minus outside. That's different from the cosine formulas. And here we have the sum and difference formulas for tangent. Tangent of A plus B, you'll notice that the plus inside gives a plus in the numerator, and the minus inside gives a minus in the numerator. However, there is also a denominator operation, and it's opposite from the numerator. So if it's plus in the numerator, it's minus in the denominator, and opposite when in tangent of A minus B. Now let's compare the cosine of a sum with the sine of a sum. Cosine of A plus B can be thought of as cosine cosine, sine sine. The sine, though, is sine cosine, and then sine cosine again, sine A cosine B plus sine B cosine A. The cosine has a plus inside but a minus outside, whereas the sine has a plus inside and a plus outside. Okay, let's put this into practice by finding the exact value of the cosine of 15 degrees. And by exact value, I mean no calculators. We are going to use the cosine of a difference. Cosine of A minus B is the cosine of A times the cosine of B, plus sine of A, sine of B. I encourage you, when you have a chance, to actually just keep practice writing these down. By the way, 15 degrees can be thought of with some familiar angle measures, 60 degrees and 45 degrees, 60 minus 45, and there are many other options. For now, cosine of 60 degrees minus 45 degrees, one step at a time, cosine of the first, 60 degrees, times the cosine of the second, 45, plus sine of the first, times sine of the second. Of course, cosine of 60 minus 45, that means cosine of 15 degrees. This is not one of our normal unit circle measures, by the way. Cosine of 60 is 1/2, and cosine 45 is root 2 over 2, plus sine of 60 is root 3 over 2, times sine of 45, root 2 over 2. We're now going to multiply these fractions together. Radical 2 over 4 plus radical 6 over 4. Now they have a common denominator, so we can combine them into a single fraction. Square root of 2 plus square root of 6. And there we have it. The square root of 2 and square root of 6 cannot combine. By the way, I recommend that you pause the video right now and you try it using 45 degrees minus 30 degrees. You should get the same answer, although yours might be square root of 6 plus square root of 2 over 4. Same thing. Okay. Now, we can use the sum and difference formulas to develop a lot of other formulas, including number 7, 8, and 9 that you see here, the cosine of a difference with 90 degrees, or the cosine of a sum, or the sine of a difference or sum of 90 degrees. We can also generate what are called negative angle identities. These include cosine of negative b, sine of negative b, and tangent of negative b. All of these identities can be generated using either the sine or cosine of a sum or difference. Let's prove one of those new formulas. Cosine of 90 degrees minus b equals sine of b. That's the cosine of the first, 90 degrees, times the cosine of the second, b, plus sine of the first, 90 degrees, times the sine of b. We can evaluate a couple of them. Cosine of 90 degrees is 0 times cosine b, plus the sine of 90 degrees is 1 times sine b. Of course, 0 times cosine b is just 0, and 1 times sine b is just sine b. And when we add 0 plus sine b, well, we get what we're supposed to get. Sine b equals sine b, QED. Okay, now let's prove that the cosine of negative b equals the cosine of b. The way we're going to treat negative b, though, is as 0 minus b. That's the same thing as negative b. And now we have the cosine of a difference. So we can treat it as the cosine of the first times the cosine of the second plus sine of the first times sine of the second. Cosine of 0 is 1 times cosine b, plus sine of 0 is 0 times sine b. 1 times cosine b is cosine b plus 0, and you can see that that's equal to cosine b, which is what we were trying to get. So again, QED. Okay, let's practice using the cosine of a sum formula, and we're going to use it to find the cosine of 105 degrees. In this case, we use 105 as 45 degrees plus 60 degrees. Cosine of a sum is the cosine of the first times the cosine of the second minus sine of the first times sine of the second. We'll evaluate each one of those. On the left side, that's the cosine of 105 degrees. And cosine 45, root 2 over 2. Cosine of 60, 1/2, minus. You can see here the sine of 45 times the sine of 60, which is square root of 3 over 2. Again, we multiply the fractions together, get a common denominator of 4, and so we can combine them into a single fraction divided by 4. Square root of 2 minus square root of 6. Now these square roots cannot combine. They are not like radicals. So we have to leave them just as they are. And now let's find the sine of 195 degrees by treating it as the sine of a sum. Now 195 degrees ends in a 5, which means we probably have 45 degrees as one of the angles. Or maybe it's 135 degrees as one of the angles. And you can see the pair of angles that add up to 195. We can use either one, and it doesn't matter which one we use, we will get the same result in the end. Let's go ahead and use the sine of 135 plus 60 degrees. Sine of the first, cosine of the second, plus inside, plus outside for the sine, sine of the second times cosine of the first. Evaluating each, sine of 135 is square root of 2 over 2. Cosine of 60 is 1/2, plus sine of 60 is root 3 over 2 times cosine 135. That's a negative square root of 2 over 2. Again, we can multiply these fractions, and you're actually going to see some familiar numbers. Get plus negative root 6 over 4. And, of course, having a common denominator 4, they can combine into a single fraction. But again, the numerator values, the square root of 2 and square root of 6, cannot combine. They are not like radicals. Okay, now let's find the sine of negative 15 degrees by using the sine of a difference formula. Negative 15 degrees is 30 degrees minus 45, or it could be 45 degrees minus 60 degrees. Let's use 30 degrees minus 45 degrees. So this is now the sine of a difference formula. That will equal the sine of the first, sine of 30, times the cosine of the second, cosine 45, minus the sine of the second times the cosine of the first, times cosine 30. So, on the right side, sine of 30 degrees is 1/2. Cosine 45 is root 2 over 2 minus root 2 over 2 times cosine 30 of radical 3 over 2. And these products are square root of 2 over 4 minus square root of 6 over 4, which is now, with a common denominator 4, root 2 minus root 6, all over 4. I just want to point out something. In this particular case, sine of negative 15 degrees. Well, the negative 15 degrees is actually in quadrant 4, and that means that the sine is a negative value. And this answer that we got, this numerator, is also negative, so it's appropriate. It's negative because square root of 2 is a smaller number than square root of 6. So radical 2 minus radical 6 is negative. Okay. Now, as with any other identity, we can read it from left to right or from right to left. We can have the cosine of A cosine B plus sine A sine B being equal to cosine of A minus B. Basically, it can be read either way. And that's helpful for us when we are recognizing a pattern. Here we see cosine of 50 times cosine of 20. Well, that's cosine cosine. And plus. Well, this pattern fits the cosine of, not a sum, but a difference. Remember, for the cosine, the plus and the minus are opposite. Inside, plus outside, minus inside. And we just use the angle measures that we see there, 50 degrees minus 20 degrees. That simplifies to cosine of 30 degrees, and we know that value is square root of 3 over 2. Here's another one. Let's see, this is sine, cosine. Okay, this is going to be the sine, either a sum or difference. And we see that the sine of 110 in the first and the sine of 170 in the second. Then cosine of 170 and then cosine of 110. So all the parts match up. All the pattern is consistent with the sine of a difference. In this case, sine of 110 minus 170 degrees. Well, that actually is the sine of negative 60 degrees. That's a fourth quadrant value where sine is negative. And sine of 60 is root 3 over 2. So negative root 3 over 2. Okay, this one starts with cosine. So you'd think, well, maybe cosine cosine, but it's not cosine cosine, as we see. That's interesting. You know what I think it is it's just written in the wrong order. So let's rewrite it, writing it with sine first. So sine of 185 times cosine of 130, and then sine of 130 times the cosine of 185. So sine cosine plus sine cosine. this pattern is the sine of a sum. So the sine of 185 degrees plus 130 degrees. And when we add those together, that is sine of 315 degrees. Let's see, that's in quadrant 4, so sine is negative. Related to 45 degrees, negative root 2 over 2. Okay, we've been working with angle measures, with degree measures this whole time. Now let's work with radian measures, and to do this we'll oftentimes need a denominator of 12. So let's look at each of these common radian values and make them into a denominator of 12. Pi over 6 we can multiply by 2 over 2 to get 2 pi over 12. Pi over 4 times 3 over 3 to get 3 pi over 12. And pi over 3 times 4 over 4 giving us 4 pi over 12. Now pi over 2, that's 1/2 pi, that's 6 pi over 12. And I'll just go ahead and fill in the last few rather quickly here. Something you can do on your own, certainly. So what you see here are 2 pi over 12, 3 pi over 12, 4, 6, 8, 9, 10, and 12 pi over 12. So how can we apply this to find the sine of pi over 12, meaning 1 pi over 12? Well, we can subtract any two that differ by 1. For example, 10 pi over 12 minus 9 pi over 12. Or 9 pi over 12 minus 8 pi over 12. 9 minus 8. Or, as we see here, 4 minus 3. 4 pi over 12 minus 3 pi over 12. Let's see how we use this for the sine of 1 pi over 12. Let's go ahead and use the 4 pi over 12 minus 3 pi over 12, although all of them that we see there could have been used, any one of them. Well, actually, the first thing we do before we expand this is to simplify each of those fractions. 4 pi over 12 is pi over 3, and 3 pi over 12 is pi over 4. And now the sine of a difference is the sine of the first, sine pi over 3, times the cosine of the second, cosine pi over 4, minus the sine of the second times the cosine of the first. Sine of pi over 3 is root 3 over 2, and cosine pi over 4 is root 2 over 2. And for the next pair, we get square root of 2 over 2 times 1/2. And again, we see the square root of 6 and the square root of 2 all over 4. And we can combine them into a single fraction. Root 6 minus root 2 over 4. As a reminder, those radicals cannot combine because they're not like radicals. Well, that's all I have for you today. I hope this has made some sense and you'll find it very helpful to you. Until next time.